Hi everyone, my name is Chuang, a researcher at MIT-IBM working in a lab. Today, I'm very excited to share our recent work on human-centric audio-visual learning. As we all know, with the emergence of deep neural network, we have this revolution on many single modality tasks, such as image classification and segmentation, video recognition, motion translation, and also speech recognition. In the meanwhile, the community also made considerable progress on multi-modality applications, including visual captioning, visual question answering, visual relationship reasoning in images, and also more challenging causal reasoning in video. In this talk, I will not talk too much on vision and language, so I know in the computer vision community, when people talk about multimodality, they mostly refer to vision and language. Instead, I would like to introduce a new frontier for multimodal intelligence: vision and sound. Actually, for a baby, though they have very little knowledge about language and concept, she can still capture the corresponding between different modality to reach a deep understanding of the physical world. How they achieve this goal? Let's first watch a demo video. So in this video, you would like to see a baby doing things that just seem a little bit random. Putting cups together, making stack, knocking them over, and hearing the clatters. Intensive evidence from cognitive science, psychology, and neuroscience suggests that this multimodal cue actually plays a key role on the development of many interesting behaviors of human intelligence. Inspired by this fact, we are interested in building AI systems that can see and hear. In this talk, I will show several exciting applications on human-centric audio-visual learning. The first application I would like to introduce is visual sound separation. Before going into any technical detail, I want to first give credit to my two colleagues, Dr. Hang Zhao and Professor Antonio Torralba. So we started working on this domain 2 years ago. The problem we want to solve is that given a performance, we're giving you a music performance video like this one. And the goal is to separate the sound played by different musicians. Let's first review how traditional audio-based approach performs sound separation. The audio-only model usually first estimates a mask for each sound component. And then they will use this mask to multiply the input sound spectrogram to separate the sound source. Yeah, the audio-only approach works well for many applications such as speech separation, but still very hard to generate to many other natural sounds, for example, the music. Our idea to solve the music sound separation is to connect vision with sound by learning from music videos. We believe a machine can learn to associate the sound component with visual signal by watching and listening many videos of human playing instruments. So we first create a large-scale music performance video dataset. We retrieve the music video from YouTube by keyword query. During the search, we add keywords such as cover to find more video that are not post-processed or edited. Music dataset has over 1,000 untrained videos of music solo and duet. The dataset spans over 20 instrument categories. We have already released this dataset. Feel free to use that for your research. So our main idea to do this visual sound separation is adopt to a mixed separate framework. Concretely, we first audio signal from different video clip. This is one example. We create the synthetic a synthetic mixture sound. And then the goal of our model is to separate the audio track from the mixture condition on their visual condition on their corresponding visual input. To be noted, even though the neural network is trained in a supervised way, but it does not require ID label data. So we consider this training pipeline as a self-supervised learning. And we also name this training procedure as mixed and separate framework. Okay, let's go to the detail. Mixed separate framework consists of three key components: a video analysis network, an audio analysis network, and audio synthesizer network. First, the video analysis network extracts visual feature from video frame that containing musician playing instruments. The audio network then converts the raw waveform into some spectrogram representation, and then using a unit style architecture to encode the audio feature into different channels. The audio synthesis network finally predicts the sound by taking visual feature and audio feature as input. The learning objective of this model is to predict a mask. The ground truth mark for each video is calculated by whether the target sound is dominant component in the input mixture sound on magnitude spectrogram. Then the predicted mask is threshold and multiplied with the input complex sound spectrogram to get the predictive sound spectrogram. Finally, we apply an inverse short-time Fourier transform on the predicted sound spectrogram to reconstruct the waveform of separate sound. During the testing phase, we can either take the raw video frame as input to separate its corresponding sound, or we can also click the pixel and take the region feature as the input to listen the sound of pixels. Okay, let's watch some demo video now. Here is the original video with two people playing different instruments. And we click the pixel of playing guitar. What will happen? Okay, how about we click another instrument? How about when I click the background? Okay, it seems nothing. Okay, let's watch another demo video. Okay, we first click the trumpet. Let's now try the guitar. Okay, let's try the background wall again. It seems nothing. So our model can definitely separate the sound components of different instruments, and also it can also learning that the background will not make any sound. Our system could also enable us to do sound editing in video based on clicking the pixel. For instance, we can do volume adjustment for specified musician, or removal of the audio from particular sound. Here is an example. So given this music performance video, we can click the pixel and do the music remix. Okay, we'll adjust the volume. And what will happen? How about we do the reverse? Okay, amazing, right? Here, we also visualize the sound that each pixel made in image using a clustering-based approach. From this figure, we can observe that different instruments and the background in the same video frame has very different color embedding, indicating different sounds that it will indicate different sounds that they are making. Okay, so very impressive performance we have achieved. But I would like to say the visual conditions are still strong enough for more challenging tasks. For example, our model can do nothing when separating multiple instruments at the same time. Here example. So what's the solution for this kind of challenging task? Okay, this is probably the reason why I want to give this talk, human-centric audio-visual learning. So in a paper we published on this year's CPR, we propose using music gesture, it's a kind of study musician body language to identify the music components. Music gesture actually is a key point-based structure implementation. We expect that based on the key point coordinate of the human body, we can implicitly capture the body and the finger movement of musicians when they perform the music. And we believe sensing the human body movements will be the key to do better sound separation. Concretely, we adopt a similar mixed separate training framework. But for the visual analysis network, it mainly contains two parts. We first take a video frame to extract the global context feature using ResNet. And more importantly, we extract the human body key point coordinate using OpenPulse API. To implicitly capture the body dynamic cues, we're using a special temporal graph network on the key point coordinate. We combine the appearance feature and the key point dynamic feature as visual condition. Finally, we apply an audio-visual fusion module to associate the body movement with the corresponding audio signal. With the strong human sensing model, our new music gesture model achieved much better results than previous SODA system. Here, I would like to show some comparison results. These results are generated by a previous SODA system named as Sound of Motion. Even though in this system it already combines appearance feature and also optical flow and trajectory-based motion feature, the model still can do nothing in this hard case. How about the result when you're using music gesture feature? Here are the results. clearly that our model is significantly better than previous system and do a reasonably good performance on this challenging task. Let's watch another example. Again, the sound motion system did nothing in this hard case. Let's see the music gesture. Okay, it seems that it's not doing perfect, but it's indeed doing good job in this very challenging task. At the end, I will show an example that I like most. We can also do piano the piano do the separation. Here's the baseline result. Again, they did nothing. How about the music gesture? Okay, quite impressive, right? And we also test our music gesture on more challenging tasks that we can how our system to separate multiple instruments. Here is the other result. Another example. Here, we also visualize the key point of attention map for understanding what our model has actually learned. Here's where we definitely observe some very interesting observation. For example, our model tends to focus more on hand key point when separating guitar and flute sound, while paying more attention to elbows when separating the cello and the violin. This definitely makes sense. Our structural key point based representation can also help us to isolate the sound of body parts. Here example. Okay, till now you have seen how something human can benefit visual sound separation. You might ask another question. So can we directly infer music based on body movements? The answer is yes. In a follow-up paper published in this year's ECCV, we introduced the new Foley music system that can generate plausible music from silent video of music playing instruments. Actually, this technique can serve as a foundation for many applications, from adding sound effects to video automatically to creating immersive experience in VR scenarios. But this is also a very challenging problem. First, we need to recognize the physical interaction between instruments and musicians from video. Second, we need audio representation that respects the major music rule and also easily to be predicted from video. Finally, we need a model to associate the two modalities. To address the challenging, we identify two key elements for a successful video-to-music generator. For the visual perception part, we again extract the key points from video frame to implicitly model body parts and hand movements. For the music, we propose using MIDI, a symbolic music representation as intermediate representation. I believe in many computer vision community, people might not be very familiar with the MIDI representation. So I gave a brief introduction here about MIDI events. So MIDI events encode timing and loudness information for each note event, such as note on and note off. Then given a pair data of body key points and the MIDI event, music generation from video can be posed as a human motion to MIDI translation problem. Concretely, we first detect key points from video similar to the music gesture paper, and then we apply a graph network on detect key point to capture the human body motion. And then we're using a transformer to align the key point feature with MIDI events. Finally, the MIDI event is converted to the waveform with standard audio synthesizer. Okay, I think you have to wait to see this result. So since the MIDI representation are fully interpretable and transparent, so it also enables us to perform the music style editing easily. Here are some examples. Here's another example. Okay, the last one. Okay, so at the end of my talk, I would like to introduce a recently released platform named as ThreeDWorld, or in short, ThreeDW. It is used for interactive multimodal physics simulation. So again, I would like to first give credit to Awesome Engineering, Jeremy and Sis, and they spent a lot of time to make this simulator happen. So with TTW, user can simulate high fidelity audio and visual data in complex physical scenes. So here is the example to show the power of the simulator. Okay, so TTW has several unique properties. Firstly, it can do real-time near photorealistic image rendering. Secondly, it has a large library of objects and environment with material for high-quality rendering. Thirdly, it has generative procedure for efficiently building class of new environment. And fourthly, it also have high fidelity audio rendering and believable and realistic field interaction for both rigid body and deformable objects. We also support a range of avatar types that can serve as embodied of AI agent. And it also supports for human interaction with VR devices. This is quite unique. Of course, so the most important part of why I want to talk about this simulator is that we can also simulate humanoid avatar. So you can watch this video. Yeah, we can do purely fairly realistic human motion simulation. So we believe that this platform will open many embodied human-centric multimodal embodied tasks. And we have already released this platform. And you can check our website. And we are happy to take any feedback when using the simulator. And again, that I would like to emphasize that the audio-visual learning is more like an emerging field. And I agree that there currently little research team and working the team, but I definitely think that incorporating multi-sensor data should be a next step for more intelligent AI system. And for audiovisual scene analysis, a very important key point is that we need to understanding and sensing the human activity. This will enable you to do much better job than before. Okay, I think I'm run out of time, and thanks for attending my talk. And also, I would like to thank the organizer that to make me here, and also to organize this wonderful workshop. So I can take some question offline, and you can email us or try and type question here. Okay, thank you.